Okay. Hello, everybody, and welcome to a new session of our webinar, AMSUD on differential geometry. Today, our speaker is Mauro Subils from Universidad Nacional de Rosario in Argentina, and he will speak about magnetic trajectories on the Heisenberg group of dimension 3. As usual, you will see many announcements in the chat of this meet, and you can find there the instructions to join our mailing list or the WhatsApp group. Okay, well, thank you, Mauro. Go ahead, please.
Well, thank you, Adrian. Thank you, the organizers, for the invitation. It's nice to be in this seminar. So this is a joint work with Gabriela Bando, also from Rosario. I'm going to speak about magnetic trajectories of the Heisenberg group of dimension 3. And the talk is organized as follows. First, I'm going to give some basic facts about magnetic trajectories, and I will fix the setting where we're going to work in the Heisenberg group of dimension 3. Then in the next two sections, I'm gonna give explicitly what are the magnetic trajectories on the Heisenberg Lie group for all possible Lorentz forces. And in the last section, I'm going to speak about the existence of periodic magnetic trajectories on the group and on the manifolds associated to this group. So the motivation to study magnetic trajectories comes from physics, like the name says. So in physics, the Lorentz force, the magnetic force, depends on the velocity and it's normal to it. So if you fix a Riemannian manifold, any Riemannian manifold, and F in a skew-symmetric 1-1 tensor that we're gonna call the Lorentz force, that verifies this condition, that the two forms associated to this 1-1 tensor is closed. These two forms is called the magnetic field. Then the magnetic equation for this Lorentz force is this, no? Where this is the Levi-Civita connection, and this is the Lorentz force. So you see that when F is 0, you got the geodesic equation. That is the movement. You have the movement of a particle without the force, no? The geodesic curves. So when you have a Lorentz force, you have to solve this equation, no? So the solution to this equation are the magnetic trajectories. Okay. So one simple fact about the magnetic trajectories is that, like geodesic, they has contact speed, no? Constant speed. But when you reparameterize a magnetic trajectory, you don't get a magnetic trajectory for some fixed f. This is because this equation is not homogeneous on the velocity of the curve. So it's common to fix an energy. So we are going to say that the energy level of the curve is this constant. No? It depends on the speed. So in some setting, you fix the energy, study magnetic trajectories with this energy. Well, in what setting we are going to work? Well, we fix the manifold, the three-dimensional Heisenberg group, with the standard left invariant metric, G, and F will be a left invariant skew-symmetric 1-1 tensor. So to remember that H3 is a simply connected Lie group of dimension 3 with Lie algebra expand these three vectors that verify this relation. In exponential, we will use the exponential coordinates in the group, and the product is given by this formula, and the identity is the 0. No? So if you don't know nothing about the Heisenberg group, you can think of R3 with this non-commutative product. No? So the left invariant metric in H3 is the one that makes this basis orthonormal. We're going to fix this metric, and since we are working with left invariant skew-symmetric, these are determined by the transformation on the Lie algebra. No? So in the basis that we fix, the orthonormal basis, the Lorentz force has this form, where alpha, beta, and rho are real numbers. So one can check that this force is always closed for any alpha, beta, and rho, and the force is exact. That means that the magnetic field associated is exact if and only if these alpha and beta are 0. This was studied a lot by Epstein, Gordon, and Math in this paper that we're going to talk about a little more. And they calculated actually for any Heisenberg group of any dimension. And we study in general, we see that in this case and in any two-step nilpotent Lie group, that you have a force that preserves the center, like the exact ones, when alpha beta is 0, the force preserves the center and the orthogonal complement. So in these cases, in any two-step nilpotent Lie group, the magnetic trajectories can be written down in terms of trigonometric function and linear function, and they are quite nice, no? But we try to study what happens when this is not the case, when the center is not preserved by the Lorentz force. So we first study the case when rho is 0, in this case, and alpha beta is different 0. And we see that in this case, you have, for example, elliptic, they appear elliptic functions to write down this magnetic trajectory. And we also, from this, we also raise the question, what happened in the general case when rho, alpha, and beta are all different from 0? So I will answer this question in the following slides. So first I want to show you how are the magnetic equation in this setting. So we see that we can restrict to the case of magnetic trajectories through the identity, because by a translation, you can, since the force is left invariant, you have a magnetic trajectory through a point G, you can translate it to pass through the identity. So all magnetic trajectories are translations of the magnetic trajectories through the identity. So we restrict to this case, and the magnetic trajectories in this, the magnetic equation translate in this form. It depends on alpha, beta, gamma, and rho. Well, we want to simplify this equation a little bit. So if you fix the initial condition on the velocity, by x0, any direction, you can simplify the magnetic equation, and you get this form, when this is the theta 0 of the initial condition. And we see that you can act, I want to simplify further this equation. So if you take an orthogonal automorphism of the Lie algebra, then you can act on these magnetic trajectories and see that if you have a magnetic trajectory of some f, the transform by this orthogonal automorphism is a magnetic trajectory for the conjugate of the f. So we see that in the case of H3, in the case of the Heisenberg group, the orthogonal automorphism of this Lie algebra acts like the rotation on this plane, on A1, A2, E1, E2. So there exists, you can rotate, you can act like conjugate the F, and see that you rotate in alpha and beta. No, rho is the same, and you rotate in alpha and beta, so you can rotate in such that alpha, this term is 0. And you can study these forces and all other forces. If you change the force, they are transformed by this rotation, this automorphism. Now, so we can assume that alpha is 0, and you get we fix this force, and the system reduced to this form. Well, now I'm gonna divide in two cases. No, the exact case is when beta is 0, and the non-exact case is when beta is different from 0. When beta is 0, the exact case, you have this system, no, this force, this system, this initial condition, and this was studied by Epstein, like I said, Epstein, Gornet, and Mass, and they write the solution of this equation, and you get these trajectories. Now it depends from the initial condition. If it's theta 0 is different from minus rho, you get this. They are like ellipses, no, the form ellipses, and you see that when rho is 0, you get the geodesic of the Heisenberg Lie group. And well, you also get some one-parameter subgroups when you have this compatibility condition. And now I want to talk about the non-exact case that we dealt. Is when beta is different from 0. So here we also make some simplification looking at this. No, if you take a magnetic trajectory for some f, you can reparameterize by in this form to get a magnetic trajectory for this another force. So you can assume that beta is 1 because you only have to reparameterize to get the other, no, for the other beta, the other magnetic trajectories. So finally, you have to work with this Lorentz force in the non-exact case, which the system reduced to this. This is a harder to solve than the last one, no? But we managed to solve it in the following way. No? We reduce it to a system of one equation on x, and this system gets you to this integral. No? You see that x is inverse of this integral, which is an elliptic integral. This is a quartic polynomial. So solving this, now I'm gonna speak with table of integrals and etc. You have the following theorem. No, in the non-exact case, you have that the magnetic trajectories are these. No, when you have also a compatibility condition when you get a one-parameter group in this case. And if it's not the case, you have this, where I'm gonna tell you in the following what is this function. No? This function depends on the initial condition, this phi, and the others are right in terms of this function. No? So what is this function? Well, to study a function, we have to study the polynomial, no, the quartic polynomial that I talk about here. This polynomial, no, the solution of this elliptic integral has to is related to the roots of this polynomial. So you calculate the discriminant of the polynomial and see that remember that when the discriminant is negative, the polynomial has two real roots and two non-real complex roots, conjugate, obviously. And you call the delta 1, delta 4, that we are going to use this, the distance between the complex roots and the real roots. When the discriminant is positive, the polynomial has 4 real roots, and when the discriminant is 0, the P has a root of multiplicity, no? Of multiplicity 2 or 3 in this case. And S will be this constant. So from this we get that when the discriminant is negative, the function phi that determines the magnetic trajectory is this one that depends on the roots, the real roots, and the distance to the complex roots. Where this function in red is the cosine amplitude. These are Jacobi's elliptic function. They are functions that behave like the cosine. They are periodic and behave like the cosine, and depends on a modulus k, which here is between 0 and 1. Can be defined for modulus greater than 1, but in general you work with k between 0 and 1. So you can write the function in terms of the roots and this distance between the roots. And the constant C1 that appear here has to do with the thing that the fact that you want to this function to in 0 be 0, no? X in 0 must be 0. So you choose this constant such that this verifies that condition. You can write it down, but it's complicated. You can lay like a constant. Well, in the case that the discriminant is positive, you have this solution that depends on the initial conditions. Here appears also the other elliptic integral function. This is the sin amplitude, like that is like the sine. Is similar. And here also you can write it down in terms of the 4 real roots. In this case, you have 4 real roots. And when the discriminant is 0, this is like the singular case, you have these 3 possibilities. Depends on the S, no, on the sign of S. If S is positive, you have it's appear the cosine, here the hyperbolic cosine, and you have a rational function here. This is 0. This is when R is has multiplicity 3. This is the case of R of multiplicity 3. Here has multiplicity 2. So in this way, we describe all magnetic trajectories, no, for the non-exact case in terms of the root of these polynomials. It's not as direct as the other case because it's difficult to write this root in terms of the initial condition, but we can study the behavior of these trajectories. Well, for example, we see that in this table, these are the cases. No, the four cases. These are the periodic ones. These are the periodic ones, and here is the period in each case, the image of X, and in these cases it's not periodic. No, this is not periodic, and this is the hyperbolic cosine is not periodic. Well, now we can describe all magnetic trajectories with this in the exact and in the non-exact case. And now I wanted to speak about periodic.
Mauro, one question. When the function phi is periodic, the trajectories are closed?
No. That is the X, only the X.
Only the X.
Now I'm going to talk about that. Yes, now I want to talk about that. Yes.
Okay, thank you.
Because you have the X is periodic, but you don't know about these two, no? So you can have like an ellipse, no?
Yes, okay. Thank you.
That the X, maybe the Y may be periodic, no, but you don't know about the whole curve. No, and now we want to study about that. No, I want to periodic magnetic trajectories when these curves are periodic, if there is, no, if there exists someone, no. In the exact case, this was studied by Epstein, Gordon, and Mass, and they see that in the exact case, for low energy, there exists periodic magnetic trajectories, no? And it's if and only if, no? If the energy is greater or equal than this number, you don't have a periodic magnetic trajectory. And they can, give more explicitly which is the condition, the period, etc. Well, in our case, it's more difficult because you have to work with this function, and with this function, no, it's not as direct to study if this is periodic or not. No, but we managed to prove the following theorem. In the non-exact case, there exists periodic magnetic in energy, in any energy level, and we can be. I want to give a sketch of this proof. To be more precise. So first observe that we are going to restrict to the case of x0 greater than 0, because if you have a magnetic trajectory from this initial condition, you can transform it to a magnetic trajectory with this initial condition. So these two curves have the same energy, and if the one is periodic, the other one is also periodic. So we are going to restrict to the case that the condition is greater or equal to 0. And well, first one sees that, like we say, you have to first we have to have that x is periodic, no? In the cases where x is periodic, and you see that the period of the curve, if it's periodic, must coincide with the period of the x. And from this, from the equation, you get this relation, no? The derivative of y is periodic if x is periodic, so you have this condition. No? And the function set depends on x and y. So what you have when x and y and z are periodic if and only if this number is 0. It's clear, no? If this number is 0, y is periodic, and if y and x are periodic, z is periodic. So the only condition you have to check is this, to see if there are or no periodic trajectories in this case. Well, we calculate this no, in terms of the solution we have in each case. For example, in the case of discriminant lower than 0, negative discriminant, you have this solution that depends on the roots, the distances, no, delta 1 and delta 4. Sorry. And E and K are non-function, are the complete elliptic integrals of the first and the second kind. These are like are elliptic integrals, are inverse of the Jacobi. They are related to the elliptic functions. Well, but to work with this, we see that these are roots of the polynomial, so it's hard to study this function because you don't have don't know in which domain this varies, no? And how is the relation with this number. So the trick we use is to reparameterize the initial condition such that the discriminant is negative, and you have this, by 3 numbers, C, D, and E, in this domain that is much nicer. No? You have this domain, and the reparameterization is given by this. No? But you see that you now can write this function in terms of these new parameters. In terms of these new parameters, the function has this domain, and depends only on C and D, and it's this function that depends in the domain of C and D, which are free variables. For each one of these, you have an initial condition. They are related. And you can study when this function is the zero of this function. And you see that for every C greater than 1, you have a unique D in this interval such that the function is null. For C less than 1, you see that this is never 0. So there are no magnetic trajectories in that case. So you get this theorem, no? For any one of these points, you can fix C, fix E, you get a unique D such that the magnetic trajectory with the initial condition given by these formulas is closed, no? Is periodic. Is periodic, and in this case, you have that these are all the periodic magnetic, because we also calculated in the cases that the discriminant is greater and equals to 0, and we see that in that cases this function never is 0. It's never 0. So the magnetic periodic trajectories appears only in this case, no? In discriminant lower than 0. And also from this we can prove that there exists at least one from each energy and of each length. This is done by we calculate the energy in terms of C, no? And the length in terms of C, and see that this function takes all values. No, it's going to infinity as C increases. No, and this is this says that you have a magnetic periodic trajectory of any energy and of any length. Our conjecture that we are working on is that this is bijective. No? So if for each C you have, for each energy you have one C, and for each length you have one C. You have a bijection. It's not easy to prove, because see that you don't have how D depends on C, because this is determined implicitly by the function, and so you have to study the behavior of this function, of the function in terms of C. So, well, now I'm going to talk about periodic magnetic trajectories on the nil manifold associated to this. So you take a lattice, no? A lattice on H3, which is a compact discrete subgroup, and the left invariant Lorentz force on the group can be induced to the quotient, no? Because of the invariance. No? Then the magnetic trajectory on the quotient arises as projection of the magnetic trajectory on the group. So to study periodic magnetic trajectories on the quotient, we have to study the next curves, the curves in the next definition. They are the lambda periodic periodic trajectories. In any Lie group, you can define for any lambda, a curve is lambda periodic if there is a period such that the curve is periodic, no, by a multiplication of this lambda, of the fixed lambda. So when you project this, you get a periodic in the quotient. Well, when lambda is in the lattice, the lambda periodic project, like I said, to a periodic magnetic trajectory in the free homotopy class of this lambda. No? The fundamental group of the quotient is this lambda. So you get a curve in the homotopy class of this element. Well, in the case of exact, was studied by Epstein, Gordon, Mass in the same paper. They see that, for example, here I give a summary. I don't go into details. For example, when lambda is not in the center, you have lambda periodic magnetic from now energy greater than this number, and you can calculate the period. But when the lambda is in the center, you have for any energy a lambda periodic, but there's differences between the conditions of the period on the initial condition. Here you have a finite number. Here you have an infinite number. Here you have only one. Well, there. I'm not going to be in details. I want to speak about the non-exact case. For speak of the non-exact case, first I want to give a general lemma that happen in any two-step nilpotent Lie group. Remember that in a two-step nilpotent Lie group, you can decompose the Lie algebra as the center plus the orthogonal complement. No, you have a metric. And in any two-step nilpotent such that it verifies this condition on the center, you see that a magnetic trajectory is lambda periodic if it verifies the next condition. No, fixed lambda. No, then C is lambda periodic. Then the component on P must lie on the kernel of the force F, and the derivative of V must be periodic of the period of the omega. So this says you that there's no, for any lambda, a lambda periodic magnetic trajectory. In the cases of here we are talking about this F is the non-exact case, because if this vector is not in the kernel, there is no lambda periodic magnetic trajectory. Conversely, if you have a curve that verifies that V, the derivative of V is periodic, and this number B in the period is in the kernel of F, this is project to the center. The kernel of F project to the center. Then the magnetic curve is lambda periodic for this lambda. So you have like a converse. But here is if you fix the curve. You fix the curve, and you see that if it is lambda periodic for some lambda or no. Well, in our case, now we pass to the Heisenberg group. Remember that the force is this. So the force projected to the center is this. So the kernel of this force is when x, the component in x is 0. So in H3, you have the solution that we gave are lambda periodic. For example, in this case are the one parameter subgroups. These are lambda periodic for any lambda or any lambda of this form. It depends on R. And when you are on the other case, which are non-one parameter subgroup, then the case where x are periodic, these are all lambda periodic for some lambda, or periodic, as we see, are periodic of lambda periodic. And in the cases where x is not periodic, this is never lambda periodic for any lambda. Well, but this is we want a stronger result, but because this gives us the lambda. You have, but in any case you have the lattice, so you want to fix the lambda. and see if for this lambda there are lambda periodic geodesic, because these lambda are given by the curve, so you don't know which lambda are these. But we managed to prove this theorem that fix a lambda, fix a lambda and an energy. If the lambda is, obviously, if the x1 is different from 0, this is not in the kernel of f of this force, f projected to c. So this there does not exist any lambda periodic for this lambda. And also we prove that if I1 is 0, there are also no lambda periodic for this case. But in any case, if x1 is 0 and I1 is different from 0, then there are an infinite number of lambda periodic for the given energy, for any energy. So we have a lot of lambda periodic trajectory for any energy. And how this is proved? Well, I'm going to give a sketch of the proof. First, observe that, like I said before, that x1 must be 0 if there is a lambda periodic trajectory. That is because of the condition on the kernel, by the lemma. The lemma, you need the E1, E2 part must lie on the kernel. So the kernel is when x1 is 0. Okay, what about the I1? Well, remember that C depends on x and y. So if you have a lambda periodic trajectory, then you have this, this is happened, the curve in the period is the lambda. So if you evaluate this expression on omega, you get this. So if E1 is 0, then Z1 is 0 and lambda is the identity. This says that is periodic, no lambda periodic. Okay. So you need to have that E1 is different to 0. So lambda is different from 0. Well, now if you fix some energy and some lambda with the condition that E1 is different from 0, you analyze the function that we gave before, the I in omega, sorry, this function, that tells you how the curves, how is the value of y in the period. So we see that if you analyze this function on curves of a fixed energy, you see that this function takes any value in a neighborhood of 0. So there exists a number, a natural number, such that this function takes this value, I1 over n. I1 is given by the lambda. So if we take this periodic lambda periodic magnetic trajectory, you have this is a lambda. Now the seed is some number, I don't know what, but this number. And if you consider this curve on a larger period, on the period n times omega, you get a lambda 1 to the n periodic magnetic trajectory with lambda 1 to the n is this number. Now you get the I1 here. I want this, but here we want the C, the C1. So to get the C1, we translate this magnetic trajectory, and translating by a G, you get a periodic magnetic for a lambda conjugate to the other lambda. So in the Heisenberg group, when you conjugate, you act on C. You can manage to arrive to a C1 by some G that depends on this C1. You can arrive to a lambda periodic magnetic for the lambda that we get. But if you take another n, a greater n, if you vary this natural number, you get another one, no? So you get a computable infinite number of lambda periodic magnetic trajectories, no? Varying this natural number. And well, these are the references. With this, I finished, no? With this, finished the proof. The reference, this is the paper of Efton, Gordon, and Mast. In this we deal with the case rho equals 0, and this is going to be uploaded soon in the archive. We are trying to finish that. So, well, that's all. Thank you very much.
Okay, well, thank you very much, Mauro. Okay, are there any questions or comments for Mauro? Enrique?
I think Viviana raised her hand first.
Viviana?
Did
Yes.
you hear me?
Oh, yes, now I hear you.
Okay, no, it was by mistake. But now that I made the mistake, Mauro, hi Mauro. I was wondering, did you use the classification of the Heisenberg Lie groups? Of the lattices in the Heisenberg, or you did it?
No, we
for this part. You don't need the classification.
No, you. Because this is for any, you can take any, and you in any lambda you have for any lattice. This result is valid for any lattice. So maybe if you want to study how in that case, maybe you have to the lattice. But we don't.
No, but it's better not to use the classification. You have the general
classification.
Okay, great. Okay, thanks.
Okay, Enrique then?
Yeah, thank you, Mauro. I have a few questions. I'm not very familiar with the motivations for, these things are called Lorentz force, and then the trajectories are called magnetic. Then I wonder, is there anything special in dimension 3 for this discussion, or is it something that makes sense in?
No, I think we are start with the simple case because it's special in the sense. Well, sorry, it's special in the case that if you are in dimension greater in Heisenberg of greater dimension, you don't have non-exact force. So in dimension 5, or Heisenberg of dimension 5, 7, no greater than 3. You don't have, this has to be 0, the beta and the alpha, to be close.
I understand, but you could study the same problem on just any manifold, right?
Okay.
How, sorry?
I'm saying you could study the same problem of magnetic trajectories given a Lorentz force on just any manifold. It doesn't have to be a Heisenberg at all, right? It doesn't have to be a solvable group. Or
No, you can study in any group.
Right? It doesn't make sense in general, right?
Yes.
So yes. In that case, if we consider, let's say we consider an even dimensional manifold, then what happens when F equals J? I mean, what happens if F is itself an almost complex structure? Then is this automatically a sort of Kähler thing?
That case, yes, there are studies where they take the Lorentz force to be the complex structure. Well, in that case, they're all exact in general.
I see. Okay.
They are of this type. We are interested in the type that preserves the center. It can be calculated in any step, and it's easy to write the equation. You have the trigonometric, the magnetic trajectory are all can be writable.
Okay.
Also.
I mean, some of it, yes.
Exact case.
Okay. But so in the example you showed for Heisenberg 3, you really find non-exact guys, right? The non-exact guys have a non-trivial alpha and beta, right? Then, well, in that case, they define a non-trivial class in the rank homology, right? And then a natural question would be, can you vary F so that omega F is the harmonic representative in its class, right? I'm trying to think of a sort of an analogous problem to other problems that emerge, and I try to find the sort of optimal omega in a given class. Now, each time you give me F that makes omega closed but not exact, then it kind of makes sense to ask what's the harmonic representative in that class, right? So if I have to deform F by some true form, I guess, right? Which one minimizes the true norm, right, in the same de Rham class? Is this something that thought about?
Yes, of harmonic. Yes, that is interesting to see. Yes, that's an interesting question.
Right, I think there's the notion of a harmonicity for F. There's a harmonic Lorentz force in the sense that the omega you get from it minimizes the ulterior energy in the cohomology class of omega. And that would be a very natural F. So every manifold would have a preferred F.
If you have
which is harmonic, and that would give you a notion of harmonicity. So this might be something interesting to study. And well, in that case, this minimal ulterior energy, which is saturated by the harmonic representative, would be a natural energy for your trajectories. So a follow-up question, which would also be natural, is: are there magnetic trajectories whole, and then are there any periodic ones below or above? There's a sort of natural energy level parameterized by the Riemann cohomology. So there might be some interesting questions, kind of non-trivial but perfectly doable, in terms of sort of variational minimizing perspective in your exact setting, even for Heisenberg 3.
Yes. See, I'm afraid that maybe the optimal force is X. I don't know how to you impose the condition that it. But maybe it's an interesting question too.
Yeah, if you impose the condition that omega is more than co-closed, then this will give you a constraint on F.
You impose
yeah, that is the condition. And then if you can solve non-trivially this equation, this will tell you what's the sort of optimal Lorentz force in that, relative to this cohomology class you started with. So that will sort of vary your initial force into another one. The reason I'm thinking about this is that I think deep inside this F or this omega is the curvature of a line bundle, and there should be a gauge transformation that puts F in its optimal form. And in that case, it would be you would be finding the harmonic representative by other means. So I would expect this to be some sort of non-trivial. You'd have to solve something like d of F equals 0 as well, right? Which is, in some sense, is also a Maxwell equation. So this should be doable, not too hard, but not trivial either. I think it's a kind of medium difficult problem, which then raises the issue of having a natural energy level to inquire about trajectories existing, right, above or below this level.
Yes.
I mean, this just on brainstorming here, but it looks like your context raises these questions, and they'd be interesting to look at.
Yes, yeah, it's interesting. I don't know.
Yeah.
Yes.
That was
it's interesting. I must go into details of that, but it's a very interesting question. Very interesting problem.
Cool. Thank you.
Okay. Are there any other questions or comments for Mauro? No? Well, if this is not the case, let's thank Mauro again. Well, and thank you very much, Mauro, for your nice talk. And I don't know how you